Hello, everyone. I'm Taekyung, and today I'll be presenting our work on spatial temporal risk-aware proactive planning with model-free environmental forecasting, advised by Dr. Woo-Jun Kim and Professor Katia Sycara of the Advanced Agents and Technology Lab throughout the Carnegie Mellon University's 2025 Robotics Institute Summer Scholars Program named RIS. Our research is motivated by real-world scenarios where autonomous agents need to operate in dangerous environments. Consider situations like wildfire investigation, gas leak detection, or monitoring radioactive contamination. In these cases, agents must get close enough to gather critical information, perhaps to locate victims or identify what's accelerating the danger. The key challenge here is that, unlike remote monitoring from a safe distance, near-field investigation exposes the agents to specific risks. The environmental hazards can damage hardware, degrade sensors, or disrupt communication systems. This creates a fundamental dilemma. The agent needs to be conservative enough to protect itself while still being capable enough to handle worst-case scenarios where some exposure is unavoidable. This brings us to our core research question. How do we plan optimal paths when the agent's safety constraints are themselves uncertain and constantly changing over time? Well, there's extensive work on safe path planning for dynamical obstacle avoidance, no prior work has specifically addressed safe path planning for spatial temporal process like fire spread or chemical plume evolution. Let me explain why existing approaches fall short for problem domain. First, for control barrier functions define rigid safe boundaries using barrier functions, while barrier functions Bx. If Bx is larger or equal to 0, it represents a safe region or safe set, and if the Bx is smaller than 0, it represents an unsafe set. However, spatial temporal hazards like fire create continuous risk gradients, not binary boundaries. This binary classification forces us into a problematic trade-off, which is either we set an overly restrictive boundaries and miss safe path throughout the moderate risk zones, it might actually be optimal, or we can use dangerously permissive boundaries that allow entry into gradually increasing risk areas. Since control barrier functions don't account for exposure time, they ignore the gradual nature of risk accumulation. And most critically, control barrier functions make control decisions based on the current state X and the local gradient of the barrier function without considering how hazards will evolve in the future. For Hamilton-Jacobi reachability analyses, while these methods can handle moving obstacles, they still maintain sharp safe versus unsafe boundaries at each time instant. Even time-varying Hamilton-Jacobi methods typically assume that the dynamics and constraints are known deterministically or follow a predictable pattern. But our premise is in that the spatial temporal risk dynamics are unknown a priori. Additionally, even without state augmentation, grid-based Hamilton-Jacobi methods remain computationally limited to systems with fewer than 6 dimensions, which is not optimal for multi-agent collaborative navigation. Next, for safe reinforcement learning faces a fundamental paradox for our problem. It requires exploration near dangerous states to learn safety boundaries, but we cannot afford mistakes when consequences are irreversible, like fire damage, chemical exposure, or system crashes. Safety filters can only respond reactively to current policy outputs in real time. They cannot proactively plan around anticipated hazard evolution patterns. And finally, generating meaningful offline training data would require us to model how risk sources evolve over time, which contradicts our core assumption that these spatial temporal dynamics are unknown prior to the deployment. These limitations point out 4 fundamental problems we need to address. First, gradual risk gradients. Real environments don't have sharp, unsafe, and safe boundaries. Risk levels change gradually across space and time. Second, model-free risk evolution process prediction. We cannot assume we know that underlying dynamics of how risks propagate. We need to learn this from observations. Third, temporal cost dependency. The cost of taking the same path changes over time as the environment evolves. Therefore, the cost function should account for these temporal dependency of the cost itself on the state. Fourth, tunable conservatism. We need the ability to adjust how conservative or aggressive the agent should be based on the situation that it's encountering. Here we see the core challenge visualized. We have an agent, multiple risk sources, and a target set the agent needs to reach. The crucial insight is shown in the comparison between time t and t+1. Notice that the cost of taking the exact same path from position 1 and position 2 is different at these two time steps. This is because the risk sources are dynamic. They're spreading, they're intensifying, and moving over time. This means our agent needs to predict how these risks will evolve. Simply knowing the current state isn't enough. So we need prediction of the risk propagation to make optimal decisions. This is where our current state of the art predictive controllers fail to address. One of the most critical challenges is that what we call local cost minima trapping. Here's a scenario. Imagine the agent finds itself in a situation where all immediate available path involves some level of risk exposure. In a naive myopic controller, or a control barrier function controller, it will identify all the neighboring risk sources as an unsafe set, surrounding itself and trapping itself inside this unsafe sets, while this safe set remains locally trapped in these regions. It seems that moving in any direction increases immediate risk, so it stays put. Getting to rotate or circle, create a circular motion planning inside that safe set and not being able to escape that set. But staying put might actually be a worse choice as risks continue to evolve around it. Our approach needs to handle worst case scenarios where damage are inevitable, but we want to minimize risk exposure. The key insight is that the damage might be unavoidable, but how can I get out of this situation while minimizing my total risk exposure? Before we elaborate on our methodology, we will elaborate on how the simulation environment was set up. We developed a comprehensive simulation environment to test our approach. Simulation includes these two key maps. One is the ground truth map, represents the actual state of the environment that the agent is trying to navigate, and the belief space map represents what the agent actually observes and believes about the environment, which includes uncertainty and noise. This distinction is crucial because in the real-world scenarios, agents never have perfect information about their environment. The following video is while an agent just follows a simple path execution without any risk-aware planning. Our simulation incorporates three critical environmental factors, which is first, the fire, second, fuel, and third, wind. The fire map, for the fire map, we use a modified far-side model with explicit fuel interaction to simulate realistic fire propagation. This captures how fires spread based on the environment conditions stochastically. For the fuel map, we model the fuel distribution using random patterns, representing vegetation and other combustible materials that affect fire behavior. Lastly, for the wind map, we generate a realistic wind patterns using multi-octave Perlin noise, which is commonly used for creating natural-looking wind flow patterns that influence fire spread direction and speed. These components interact dynamically, creating a realistic and challenging environment for our agent to navigate. The dynamics of the propagation process of each element are not provided to the agent. Therefore, it's only a property of the ground truth environment. Here, G represents the fuel modulation function, and H represents the wind-influenced thermal radiation from neighboring fires. Our agent is equipped with three types of sensors corresponding to each risk source, which will have a limited field of view. The fire sensor measures fire intensity for all grid points with the agent's field of view. The wind sensor captures wind vectors across the observable area, and the fuel vegetation sensor assesses fuel levels in a visible region. Importantly, all sensor measurements include zero mean Gaussian noise, simulating real-world sensor uncertainty. This means that the agent must make decisions based on noisy partial observations rather than perfect information. Now, the limited field of view forces the agent to create three distinctions of the areas that it observes. First, notate as BFOV, or belief space of the field of view. It's the current most reliable source of data. The past belief in the field of view space is the data that has been outdated, but since we have observed it, it has some kind of confidence in those measurements. And the black regions are the regions that we have never observed before. And all of these constitute the global belief map. Our proposed algorithm addresses all four fundamental problems through an integrated approach with key four components, starting with the current agent state and environment ground truth at time t. We have the first component, which addresses gradual risk gradients through our risk cost formulation. Component 2 tackles model-free risk evolution prediction using our spatial temporal predictor with horizon h. And component 3 and 4 are also handled by the sampling predictive control, which the cost functions explicitly address the temporal nature of the risk. Let me walk through each component in detail. For our spatial temporal predictor, it uses a hybrid CNN and convolutional LSTM architecture design for environmental forecasting. The input consists of the multi-channel observation data arranged around both spatial and temporal dimensions. The spatial encoder uses CNN nairs to capture spatial patterns in the current environmental state, and the temporal encoder employs convolutional LSTM layers to model how these patterns evolve over time. Finally, the outpainting decoder predicts future evolution states across our planning horizon H. We train these models using the multi-component loss, using which is sophisticated multi-component loss function that goes beyond simple prediction accuracy. Our loss includes four key terms. First, which is the mean square error loss, measures the basic prediction accuracy along ground truth future states. Second, physics-based loss enforce fire fuel consistency, meaning that we penalize predictions where fire exists without corresponding fuel, ensuring our predictions respect fundamental physical constraints. Third, temporal smoothness loss, ensuring our predictions don't exhibit unrealistic discontinuities between the time steps, promoting realistic temporal evolution patterns. And finally, boundary consistency loss, maintaining smooth gradients at boundaries between observed and predicted regions, preventing artificial discontinuities that could mislead the path planner. This multi-component approach ensures our predictions are not just statistically accurate, but also physically plausible and temporally coherent. For our controller, we use model predictive path integral control as a sampling predictive controller to generate optimal trajectories. The process works as follows. First, our spatial temporal predictor generates H rollouts, the predictions of how the environment will evolve over the planning horizon at the specific state the agent is located at. Then we sample multiple potential trajectories and evaluate each one across these predicted future states, meaning that each location of the cost of the state of the agent throughout the whole rollouted trajectory lives in a different time stamp or time iterations. Then the controller optimizing the two types of costs, the global costs, which measures the distance of our target, and the safety costs, which we'll define in the detail next. We apply these in a receding horizon control fashion. At each step, we recompute predictions and replan our trajectory based on the new observations. In the weightings, MPPI uses a Boltzmann-like exponentially weighted average, which which the lambda gives more weight to the lowest cost samples. A risk-aware cost function captures two critical aspects of navigating dangerous environments. First, we measure the total damage incurred by moving through at each path increment. This accounts for the immediate risk exposure from traversing through dangerous areas, explicitly stating the damage that the agent will receive by moving on through those patches. This cost function is expressed with a saturated linear function in which the damage cannot be, in order to prevent the formulation of the damage being infinitely increasing while we saturate it into a maximum intensity value. Second, and crucially, we include the change in riskiness, which is essentially a running cost that quantifies how much more dangerous the agent's position become by taking each action. These are both expressed by the risk surface, which is the values of the intensity over the distance from the center grid, and the distribution of these values are used to gain the expectation and the conditional value at risk of these distribution in order to observe how the next patch that we're going to move to are more risky in average, and also what the worst case would be for the worst case 5%, what the damage will be in the worst case 5% by moving on to that specific patch. This second component is vital for handling worst case scenarios. Even when immediate damage is unavoidable, we want to choose actions to move us toward less risky positions over time. Our cause function automatically adopts its behavior based on the situations where there are two most cases, which is the normal case where the path with no damage exists, and the worst case, which the damage is irreversible. When damage-free path exists, the major discriminator becomes the risk reduction or the damage cost, which the agent prioritizes path that minimize risk exposure or damage exposure and successfully avoids dangerous areas. In the worst case, when the damage is irresistible, meaning all of the available path involves some kind of risk exposure, the cost function shifts its focus. Here, the major discriminators become finding the path when the lowest average risk and minimizing the worst case risk exposure. This adaptive behavior is crucial for handling the local minima trapping problem I mentioned earlier. Instead of getting stuck when all options look dangerous, the agent can make intelligent decisions about which risks are worth taking. In terms of results and discussion, first let's evaluate our spatial temporal predictor. We measure performance using three metrics, which first, if you look at the extrapolation loss, it shows how accurately our model predicts future environmental states compared to our ground truth evolution, showing how the training loss and the validation loss curves converge pretty well. And the mean absolute error across all the patches for the predictions also converge very well for both the training and validation processes, meaning that it's able to successfully learn and predict complex environmental dynamics without requiring explicit physical models. The diagram on the right shows both spatial validation and temporal validation, where it demonstrates that our model correctly captures spatial patterns in the expanded field of view, and also with the horizon h=2, it shows our model's ability to predict environmental changes over the planning horizon is pretty accurate. In terms of the navigation performance, this graph shows that the target set reach rate, essentially how often the agent successfully reaches its goal. Our proposed sampling predictive control approach significantly outperforms baseline methods that rely on simple safe, unsafe boundary classifications, showing that our approach reaches its goals, its target set in 100% in all times, while the basic MPPI approach only succeeds in the 20%. The improvement comes from our ability to handle gradual risk gradients and temporal dependencies. While binary classification methods either fail to find paths by being too conservative or expose the agent to excessive risk by being too permissive, our approach finds the optimal balance between the two. Even more interesting is how we handle the local minima trapping problem. So for our naive myopic controllers, the naive myopic controllers get trapped, as explained before. When surrounded by risk, they loop around indefinitely, waiting for the risk sources to clear out. This wastes time and potentially exposes the agent to more total risk, while our worst case handling controller takes a fundamentally different approach by following the tangential value risk gradient, actively exploring available options, and finding the path with the least risky exposure. The key insight is that by considering temporal risk evolution, our agent can make intelligent decisions about when short-term risk exposure leads to better long-term safety outcomes. The overall performance shows, in terms of the risk exposure comparison, shows the dramatic reduction in risk exposure achieved by our approach. From the graph below, you can see that the cumulative damage over time is extremely larger for the basic MPPI case compared to our enhanced MPPI case, as you can see in the left too, from the behavior of the video. The improvement comes from our algorithm's availability to anticipate risk evolution and make proactive decisions rather than reactive ones. By considering how risk can change over time, we can choose paths that might seem suboptimal in the short term, but lead to much more better long-term safety outcomes. From this work, we are pursuing several exciting extensions to this work. First is context-based automatic weight adjustments of sample predictive controllers using reinforcement learning, in the sense that we want to automatically tune the conservatism level based on the specific situation rather than requiring manual parameter settings. Second, dynamic target set assignment based on information gain is for scenarios like search and rescue. We want to dynamically choose targets that maximize information gathering while maintaining safety of the agent. Third, multi-agent collaborative navigation will extend our approach to coordinating multiple agents, allowing them to share risk predictions and coordinate safe exploration strategies, as the prediction of the environment of the spatial temporal predictor is estimated to perform very well when you have a larger context for the field of view size. Last, for the real-world validation, we're planning on validation on a swarm of UAV deployments in an actual environment with risk sources, moving beyond the simulation to real-world testing. In summary, our spatial temporal risk-aware planning approach successfully addresses fundamental limitations in existing safe navigation methods. And by combining model-free environmental forecasting with risk-aware control, we enable agents to operate safely in dynamic and uncertain environments while still accomplishing their missions. Thank you for listening. And this is the 2025 risk presentation of the research by Taekyung. Thank you.